Alright, so we're going to be doing part C of this problem, this free response. And the reason why I didn't, or why I paused the video, is because I found a programming error in my TI Nspire, and that's because I programmed something in it a while ago, and that actually affected the domain thing in the statistical regression analysis. So, I would suggest doing that for this specific problem. I mean, the way the College Board does it is kind of annoying. It really doesn't, it's not as intuitive per se. Oh, I dropped my pen. It's not as intuitive per se. But I'll do my best trying to explain why and how it works to even begin with. Okay, so for part C, we have, and by the way, I can't write on this PDF. There was a program on the sidebar that allowed me to do it. But anyway, so for part C, we have to find the time at which the glider makes contact with the bumper at the far right. So pretty much the only thing we know is it's going to hit the bumper in 2 meters. And we have the graphs of both functions at some point. So I'm trying to attempt to draw a sketch here. So this is till t equals 1. And then we have a graph of the actual thing. So it goes, oh no, it's not. Okay, hold on. Come on. Okay, as you can see, it's not the best, but so it's curving upwards, and then it becomes a straight line later on. Now, if we look at this area becomes more linearized. So this whole thing is more linearized, and I should have made this blue. Alright, there we go. So, at t equals 1, around t equals 1, roughly, we have a linearized integral. So, to find the time at which the glider makes contact with the bumper, well, we know that it goes at 2 meters, and I know my pen is really not that calibrated for this problem. It's just messed up. At t equals 2 meters, I don't know why this is so messed up, but there you go. At t equals 2 meters, that's pretty much our only information we have so far. And that's, or yeah, not t equals 2 meters, that's our distance. That's how much we know, so that's when we know it will stop. Now, we have to understand the tricky thing the College Board wants most people to miss is that when you look at the function as a whole, this part is linearized. So the distance and time that the distance in comparison to the time is much different than the velocity than the distance compared to time for this section. This section, it's becoming a lot more exponentialized, while this section is linearized. So it's important to distinguish between the two. So what I'm going to do is, I know this sounds weird, this is why I really don't like the College Board's method. I'm going to label D1, D2, and I'm going to set those two variables equal to 2, where D1 is this distance. My pen is just D1, and this is D2. When you add those two distances, you should get 2 meters. Now, you might be wondering, well, this is really counterintuitive. How would I get this by myself on the actual AP? That's exactly my point. It's not very intuitive. So now we have to separate these into 2 sections, and we need to find a way. How do we get time? How do we just get time? How do we even get time to begin with? Well, the first thing we know is we can approximate this actual value. We can find this actual area under the curve by approximation. That's why, again, I really am not in favor of this technique. You can technically, technically you can divide these. So you have, okay, because I don't have, my pen doesn't work on the PDF, you'll have to try doing a little bit of visualization. So imagine this graph is projected here onto this graph I have, part A. You notice in my past clip, you notice that this curve fills in 3 boxes worth of area. It's going to fill like this. So if you can imagine, it's going to go like that. That's going to fill roughly 3 boxes. So if you take the area of those 3 boxes, you're going to get displacement. And if you take that from 0 to 1, that gives you the displacement from 0 to 1. So we know d1 as being the following. It's going to be the area of those 3 boxes. Now I really can't write this qualitatively because I don't have it on there, but you get the point. And when you actually go through and do the calculations themselves, you'll get 3 times, well, the area of one box is just 0.125, and 0.125 meters. And that's pretty intuitive because, and you get 0.36 meters for D1. That's equal D1. Now I'm going to explain why this is really intuitive. So you take the area of one box. Well, if you go by 1, we established earlier that the unit on the x-axis, the area for one box is 0.5 times the height, which is 0.25, and that gives you 0.125. So that's why 0.36 meters is D1. Now we have to find D2. So let's put a circle here. Now D2. So we need to find. So to find D2, we have to be kind of clever. So we know that delta V, I know this is pretty basic, but delta V equals delta X over delta T. Or if you really want to go fancy, dx over dt. Or V equals, not delta V, V equals dx over dt. So now what we need to do is find d2. And as we know, velocity is equal to dv over dt, or delta x over delta t. All we really need to do now is find a way to find d2. So if you really think about it, you know that d2 is going to be equal to, if I can just do this, so d2 is equal to v delta t. And because you know that, you can say that v times delta t, well, you know that delta t is just, well, here's the tricky part though. T isn't 2 seconds. That's what we're trying to solve for to even begin with. But it's not only t by itself, it's t minus 1, because we already counted the t minus 1 from the 1 is accounted for. There's that little extra, from 0 to 1, that time interval is accounted by d1. So v is unknown, but if you really remember, that's why I pulled this up, you know that at t equals 1 second, the velocity is 0.5. Again, why are we, and this is, I find this method to be kind of counterintuitive in my opinion. The regression analysis gives you the same answer, but whatever, it's College Board. You have to deal with it. So you have 0.36 plus v, we said it was 0.5, times t minus 1 is equal to 2. If you solve for t using basic algebraic manipulation, your final answer is 4.3 seconds. Again, pretty counterintuitive, but that's the way they solved it. Now, I got the same answer using regressional analysis. I think personally, it's much more faster and it's less time consuming. I think I'll post a separate little clip based on that, but until I get my calculator to work, to unprogram, I have to mess around with my calculator to get the regressional analysis working. And I can't find an online TI Nspire CX to show an example anyways. So yeah, that's how they did part C. Again, I would think that this would be the hardest. To be honest, I think this is the hardest part of part 1. But yeah, there's 2 ways to do it. So now let's do part D. Yeah, part D. Alright, part D is pretty easy. Oh no, I cannot use green. That's the color I use when I find the final answer. Okay. So part D. So calculate the force constant of the spring. Okay, so let's try kind of remembering. So we know Fs is equal to negative kx. And we know when you integrate a force, you get kinetic energy, potential energy, etc. So you get energy, and you get the energy of whatever you're talking about, the energy of a system. So you get 1/2 kx squared. Perfect. And that does not look like an x squared, it looks like 2x. So we get P E S equals 1/2 kx squared. And we also know that in addition to knowing PE is equal to 1/2 kx squared, we also know that the kinetic energy as well is equal to 1/2 mv squared. And you can do the 1/2, you can do the big equation for kinetic energy and work in, work out, but virtually in all cases you're going to set these equal to each other. So you have 1/2. So okay, can we all just admit that the 1/2 cancels out? When we set these two, we know that by conservation of energy, these two are going to be equal to each other by the big energy equation. We don't have to go through all that mess. Especially during a timed test like this, you're not going to really set it up like that. Plus, when you set these equal to 1/2 to each other, the 1/2s are going to cancel anyways. So you have mv squared, and we all know that's the initial velocity, equals kx squared. Now, to solve for okay, so here's this kind of the dumb thing. They say they're talking about force constant, but really that's just a spring constant. I mean, it's a constant. The only constant here, yeah, duh, there's mass, but k is the only other constant here. So we can solve for k by just dividing, basic division. So mv squared over x squared is equal to k. Now we plug in our values. So k is equal to the mass. Well, if we really remember, we remember that the glider the total mass is 0.4 kilograms. So we have 0.4 kilograms times. Okay, so now let's get back to the velocity. That's going to require a little more thinking. We know our total change in x is going to be 0.25. Square that. And let's see. So what did it say initially? Yeah. Okay, yeah. So what do we have? Yeah. So you have 0.25 being our change in x. That's how much the spring is compressed. That was already given to the problem. Sorry, I kind of blinked out there for a second because I thought I had to do something over here, but no. They already tell you how much the spring is compressed. All right, we're looking at this from here to here. We're looking at that case. So now that we know that, we can do, so that's 0.25. That's already given. Now, so in terms of 0.5 as being the velocity, what we have to understand is, if you look at the graph, or look at the question. Let's look at the question in very close detail. We know that at time t equals 0.79 seconds, the glider loses contact with the spring. So that initial potential energy stored must equal the final kinetic energy. That final kinetic energy is the final velocity. Now, if we look at this table, it's pretty hard to discern that 0.7, what value the velocity might take on for 0.79 seconds. If you looked at the graph, however, it's so close to 0.5, we can just say the kinetic energy is 0.5 anyways. And so when you plug that all into your calculator, you should get 1.6 Newton meters. And make sure you always include units on the actual EP. Boom, there we go. All right, that's part D. Now we're looking at part, is that it? No, we still have one more. Experiment is run again, but this time the glider is attached to a spring rather than simply being pushed against it. Determine the amplitude of the resulting periodic motion. Okay, so this is kind of delving into stuff we don't know, but at the same time, it's stuff that we know. Because I think this is a unit we're going to do very soon in AP Physics 1, but it should be fine. Okay. So, when I see amplitude and period, we learned that quite a while back. So I'm looking back at the equation sheet. And what we do know is, well, actually, you know what? And I'm starting to think about it. Right now, and I think it's just 0.25, really, isn't it? 0.25 meters? Because if you think about it, when the glider is attached to the spring, and instead of being pushed against it, I mean, the spring in itself has an oscillation of 0.25 to even begin with. I mean, I think that's kind of inherent. Yes, the student doesn't push, and while the student doesn't push against it, I mean, I would say that it's going to have a period of 0.25 anyways. An amplitude of 0.25 anyways. Yeah. And I think that, to me, that kind of makes sense inherently, but I think when we get to oscillations and such, that'll make more sense. But if you kind of think about it in the past problem, yes, they say that I'm going to admit, they don't say that it's being pushed. I mean, they say that it's not being pushed at all. The spring is free to, move around. But we don't know where the glider is being attached to. It could be attached to, for all we know, it could be attached to 0. It's attached, or actually, you know what? It's attached to 0 meters. The reason I'm kind of stuttering with this problem is because I'm kind of just thinking about this on the spot, and I really think that it's not going to matter anyway. I think it's 0.25. And I checked, yeah. So the period of oscillation of the resulting periodic motion. To be honest, I think this is a plug and chug, because if we look at the formula sheet, we can find, I remember, wasn't it? Here we go. So the period of a spring is equal to 2 pi, the square root of the mass divided by k. We have all of those values. So literally, this is a plug and chug problem. Yay. Less time wasted on the AP. TS. I'm sorry, that's a S. And I'm going to erase that. So TS, let me just erase this really quick. TS is equal to the square root of, well, the mass we know is 0.4. All right, the mass of the block, that's just pretty self-explanatory. And K we just found out was 1.6. And then we multiplied that by 2 pi. We should get 3.1 seconds. So that's it. So now we're looking at, okay, so we're finally done with problem number 1. That took a while. But hopefully these problems should be a lot easier. Okay, so a box of mass m is initially at rest is acted upon by a constant applied force of magnitude Fa, as shown in the figure above. The friction between the box and the horizontal surface can be assumed to be negligible, but the box is subjected to a drag force of magnitude kV, where v is the speed of the of the box and k is a positive constant. Express all your answers in terms of the given quantities and fundamental constants as appropriate. Okay, I'm going to make a whole new page for this. So I think this is going to be our strongest point. You know, free body diagrams, objects, and such. This problem was a little weird though, because especially I think the hardest part of this problem was just finding the time. I really think that was just it. Other than that, I think everything else was self-explanatory. So, for part A, so 2A, so this is our dot. We have f of A. Alright, I'm making this very annoying. And so it's a constant applied force. Now we need to know if everything on the right is equal to everything on the left. First, let's do our mg and Fn, and then we're going to have, okay, so drag force is kV. Now, the thing is, what you need to understand is, okay, so now, so we just need to find, so the thing with drag you have to understand is time is an important factor. In the beginning, the drag might be so small you can't even see the vector. But maybe after 1,000 or 1,000,000,000 seconds, you know, when you go to an extreme magnitude, the drag force is going to be so close to f of a, sub a, that you can basically set them as equal. So I think on the AP, I think they don't really give you a time here. They don't give you any specific value. They don't tell you if it's towards the beginning, towards the end. So I'm going to say that drag force is equal to f of a. So we're just going to put, oh no, I did a little jitter there. So this is what, k times v. F sub d is equal to kv. Alright, and when you're making the free body diagram, don't include this, so not included. Okay. So now write, but do not solve a differential equation that could determine the speed v of the box as a function of time. If you need to draw anything other than what you have shown in part A to assist your solution, use the space below. Do not add anything to your figure in part A. So again, that's why you're not including f sub d. Alright, so now what we're going to do is it's pretty self-explanatory. We need to write a differential equation. A differential equation is just something that you write with derivatives in it that you need to integrate to solve for a higher order variable. So what do I mean? Well, to find the speed v, well, v is kind of given there, and we need to define it as a function of time. So this is kind of a memorization aspect, but you need to know that kv is equal to f sub a, which is also equal to ma. Now, the thing you really need to kind of realize here is this is only in an extreme case. So what I drew in the free body diagram, I drew this as a way of saying this is the extreme case when, you know, in a billion seconds or whatever. And I also can't, so, shoot, now that I realize it, I'm sorry, I screwed up. I'm going to erase this. So what we really have is BV. I'm going to erase all of this. Oh, this is so So FA minus KV is equal FA minus, sorry. Oof, I need to be quicker on these videos. FA minus KV is equal to MA. And we know that FA is equal to, or minus, KV is equal to M. Okay, pause. Let's pause for a second. We have our velocity. We need time. How do we get time out of acceleration? dV over dt is our solution. So we don't need to solve it. So our solution, final diff EQ, and I think usually for these problems they ask you to evaluate. They're going to ask us to solve it anyways, but minus KV equals M dV over dt. This is why I don't like using this smartboard. Alright, so part C says determine the magnitude of the terminal velocity of the box. Well, terminal velocity. What's terminal velocity? That's when F sub A is equal to KV. That's when the drag force is when you're falling when you're falling out of an airplane. You're going to reach a constant velocity because of air resistance. And that is factored in with your mass, your surface area, and whatnot. But just simplify it. What we're really looking at is, and there's a huge equation they'll give you on the AP Physics C test, but we're looking at, it's just KV is equal to MA. Shoot, no, sorry. It's F sub A minus KV is equal to MA. And A cancels out because we're looking at A0 because this is terminal velocity. So when you solve for V, V is just equal to F sub A over K. We can put F sub T. Right, there we go. Now use the differential equation from part B, so that's C. Now we're looking at D. From part B to derive the equation of speed of it. See, I knew it. They're asking to solve. They're asking us to solve for the differential equation as a function of time t. Assume that v equals 0 at time t equals 0. So that's our plus c. When you're integrating, there's something called a constant. When you, just to very briefly give an explanation, if you have the function y equal, this is a function, right? When you take the slope of this function, so let me just find a linear. Let me do this with a linear function. This video would be long done if I had a working pad. So you have a linear function. You take its derivative, you're going to get, you find the slope at any point, or you find the slope for this function, you're going to get a horizontal line of some slope. Doesn't matter. Take the slope of this, a line parallel to this line, you're going to get the same horizontal line. You take a slope of something to negative infinity, negative a billion, plus positive 1.5, it doesn't matter. you're always going to get the same slope because all the lines are parallel. These lines are all parallel. All right, just imagine these lines are parallel, and their y-intercepts are the only thing that's different. Well, y-intercepts don't matter when you're taking the derivative of a function. So that's why plus c. That's why at v0 at time t equals 0. That's why it's important to know that plus c in this case in the future is just going to be 0. So we don't have to worry about that. Okay, now the fun begins. Whew. All right, let's do this. So our original equation from part B, FA minus KV, if I recall, and I think that's dV dt. Right? Isn't that's what we had, right? Nope, that's too far. Yes, that's what we had. Awesome. Okay, so now we have to solve. We need to get v by itself. Now we have to separate variables. We have to get all the dt's on one side and all the v's on one side. So we have 1 over m. Actually, I don't think I should go too far. So let's separate our variables. So we have FA over m is equal to, oh shoot, I'm making algebraic mistakes all the time. I'm doing this. Alright, so what we're going to do is try doing the drag force problem in the 2013 free response. And I decided to make a little separate clip of this that I'm going to attach into the overall video because I think this is one of the tougher concepts to learn in AP Physics C. So let's get right to it. So use the differential equation from part B, which is the stuff that I did previously, to derive the equation for the speed v of the box as a function of time t. Assume that v equals 0 at time t equals 0. Alright, so we already solved part B in the form of f sub a minus kv equals m dv over dt. And so really what they're asking here is just to solve v by itself, without any dt's, without any, just to find v by itself. We don't want the derivative of v with respect to time, we just want v. So whenever they want you to solve a differential equation, you're pretty much going to want to integrate. So this shouldn't be too difficult. I think the only issue with these problems is there's a high chance that you can make a really dumb mistake. So I think that's what gets most people. And you know what? Actually, you can earn a lot of your points just by setting up the right equation and just by showing, hey, I know how to integrate, just by doing a simple manipulation of variables. You can get most of your points just by doing that. So there's not much to worry about here. Alright, so I kind of did a little bit of algebraic manipulation, and all we're really going to do is try to, alright, so what we're going to do is integrate both sides. So, integrating both sides, we get the integral of 1 over m dt. Yes, that's an m. That's an m. And it's in green, of course. Of course. Just brighten up my day. Over 1, the integral of 1 over f sub a minus kv dv. Okay, here comes the tricky part. Or we're trying to get v by itself, correct? And before we even do anything, when you're integrating like this, you want to make sure that you have you want to have your boundaries set. So when you're looking at time, when you're taking the integral, over here, I'm just going to go from 0 to t. I mean, it's pretty self-explanatory. You're going from 0 to some time t. Here, we're talking about velocity. We're talking about v sub 0 to vt. Now, here's the issue, or it's not really even an issue. If we remember, v sub 0, isn't that really just 0 to even begin with? Because if you remember, alright, if we remember, and this is a really important thing to kind of remember. If we remember, I can't really draw across the screen. The box is initially at rest. So that's just going to go away. Now, let's actually do the math here. When you 1 over m is just a constant. The mass is always the same. And we don't see any variable t here. So this really is just going to be 1 over m, or yeah, t over m, right? Because when you integrate a constant variable, when you're integrating something like a horizontal line, you're going to get a line like that. So you're going to get t over m from 0 to t. All right. And we don't have a plus c here because that we already established. I think I already said this, but they said plus c was 0. And yeah, and it started at rest anyways. Okay, enough rambling. So I guess this is the trickiest part, trying to integrate something like this. Alright, let's think about this very carefully here. This is a part where most students tend to screw up. I'm going to extend the page here. How do we integrate this mess right over here? Okay, so the first thing you need to realize is when you're doing a drag force problem, you're probably going to have the natural number e somewhere as a function of time. And if you do remember, you're going to have to exponentiate both sides anyways to begin with. So we know somewhere here we have to get a natural log. Alright, so we know we have to get a natural log out of this thing. But to integrate a natural log, you have to have the function and its top in the denominator and its derivative in the numerator. F sub a we can just say is a constant. So taking the derivative of a constant is 0. Minus kv, well, v is our actual thing we're trying to integrate here. And I'm really not seeing it coming out anywhere. But we can still integrate this. We just need the negative k somehow. Because this is kind of a linear expression. When you take the derivative of a linear expression, you're going to get a horizontal line, or a constant. So really, I'm going to do this in a different color. But the thing is, when we take the derivative of negative kv, we're left with negative k. But we don't have a negative k up here. So we're going to try adding a negative k up there. Now we can't just add a negative k up there. That would be breaking the rules. And I wouldn't want Mrs. Wilkie coming after me. So what we're going to do is, we're going to do negative 1 over k. We're going to multiply it. Because see, when you can take it into the integral, and the negatives will cancel out, and the k's will cancel out. So now we're left with negative 1 over k. And by the way, the reason that we don't have a v up here is because the v goes away. This is what we're doing it with respect to. It's like having negative 5x. Take the derivative of that, you get negative 5. This x is represented by v. So now we have the following: negative 1 over k times the natural log of, okay, well, it's the bottom. It's just the bottom. Nothing more, nothing less. F sub a minus kv. And in that beautiful handwriting, we have that going from 0 to vt. Cool. Now we just need to plug in our boundaries. Well, this is really just t over m, right? Because, well, plugging t into t is the same thing. It makes this the same expression. Plugging 0 into t over m, where t is your variable, is just that just makes the whole thing 0. So that's just t over m. And you're left with negative 1 over k. Okay. Haha. This is where things might get a little tricky. So the first thing you need to realize is don't assume, unlike here, don't assume, shoot, and I forgot my boundaries in the previous thing, but that's fine. Don't assume that just because you have a 0 in the boundaries, this is another mistake from what I see, is this is a mistake that happens a lot, is don't assume that just because you have 0 as a boundary that your other part of your result is going to be 0. That's a special case with here, but we have to be really careful about here. So we're going to have the ln of, well, what do we have? Let's factor out that negative 1 over k. Okay, it's going to be really messy, but f of sub a minus k v sub t minus ln of, okay, well, we plug in 0 now. We plugged in vt here. Now we're trying to plug in 0. So that yields ln of f of a, f sub a. Alright, now the AP might do this. This is another important trick to realize, is that the ln of a minus the ln of b is equal to the ln of a over b. It just makes your simplification a lot easier. So that's something that you just need to know. It's just something you know for the physics C. And this is what's going to really separate the 5s from the 4s. It's going to be the people who know these little tricks for the AP. So t over m is equal to the negative 1 over k of the ln, and all this messy writing, ka minus, oh shoot, not ka, f sub a. I'm sorry about that. You know what, I'm just going to erase this whole thing. Let's not even go back. Left with 1, or t over m, my bad, is equal to negative 1 over k, the ln of f sub a minus k vt all over f sub a. Alright, that seems to be it. Now, here comes the interesting part. We now need to find v by itself. We have our vt, don't we? I mean, wasn't that the objective of this entire problem to begin with? So, we're looking for, oh no, now this is really time consuming, and I don't have an eraser on me. Great. I guess we'll just delete it. Can I delete this? Yes, no, yep, okay. We were trying to find v to begin with. Now that we have it, so here, that's what we're trying to solve for. Now we have that. We have v to begin with. We just need to isolate it. So we have v as a function of time. We just need to isolate it. And this is, I guess this is pretty easy to do. So we're just going to multiply by negative k, and we're going to get negative kt over m is equal to, well, this mess. I'm not going to write it out because that would be time consuming. Okay, so we have this ln blob. Now, how do we get rid of this ln? Well, remember, what did I say about finding, or how we always have e to the power of something? Well, there you go. That's all we need to do. So we're going to, I don't know what color should I use. I'm going to use purple. E to the power of negative kt over m is equal to f sub a minus kt, come on, kvt. I'm sorry. I'm getting better at using a smartboard, but still, I have a lot to improve on. Over f sub a. Okay. Now it's all a matter of algebraic manipulation at this point. So, what we're really going to do, so the first thing we really need to do, though, we could I guess we could multiply by f sub a, and we'd get f sub a times this is equal to f sub a minus k vt. But I still think there's a better way to approach this. We can really just simplify this term, this whole chunk of information, by just dividing. So what we're going to get is e to negative kt over m is equal to 1 minus kvt over f sub a. Now, at this point it's just basic algebraic manipulation, but this is the preferred way the College Board wants it. You could multiply by f sub a, and you could solve for v this way, but I think this way is better if you want to make sure you 100% you earn all your points. So now we are left with, so we're gonna subtract, we're gonna have to subtract 1, and then we're gonna have to multiply both sides by -1. I'm gonna show all the steps just so we're clear, but I'm gonna put a negative is equal to k vt f sub a, and now we'll multiply this negative out, and so we're going to get f sub a times e negative f sub a times e negative, oh no, now I'm doing double e, e to the power of e. And now what we're going to do is multiply both sides by f sub a. And the way we're going to do that is we have, or let's evaluate the negatives. So we're going to have negative e to the negative kt over m plus 1 is equal to k vt over f sub a. We multiply that out on each side. We're going to get f sub a over, or maybe it's a little too early that I do that. I went too far ahead. My bad. We're going to have negative f sub a e to the negative kt over m plus f sub a all over k, because we're dividing, right, to get vt. Now, the thing the College Board likes to do is they love it when you factor things out. And it really makes sense, because the next question is going to ask you to use the formula you got relating velocity to time and kind of just analyzing it. And it makes your analysis a lot easier if you have it simplified. So what we're going to do, I'll use green to write my final answer. You're going to have a final result of, and that is not green, that is black. V sub t is equal to, okay, what do we have in common here? We have an f sub a, oh, and we have a k. All right, so we're going to have f sub a all over k times, okay, well, we still have a negative e to the negative kt all over m, and I'll write that in parentheses just so we're clear, plus 1. Bam, that's your final answer. And so this is going to lead directly to the next question. I think this is it for number 2. On the axis below, sketch a graph of the speed v of the box as a function of time t. Label any intercepts, asymptotes, maximum or minimum with numerical values or algebraic expressions as appropriate. Okay, so initially you're going to have a velocity of 0 because they said the box starts at rest. And another thing I like to do is I like looking at both ends of the spectrum, right at the beginning and right into infinity. So let's really think about this. If we plug in a huge number over here for t, we're going to have, because if we really think about this, isn't e to the negative kt over m, yes, I know there's a negative, but just listen for a moment, e to the kt over m, you're going to have a huge number here. E to the power of a huge t is a huge number. Now 1 over a huge number approaches 0, as we know from limits. This negative number is going to be, I guess you could say, a smaller negative number. If you take the absolute value of this is going to be a smaller number. A smaller number plus 1 means that this expression is going to reach 1. f sub a over k is a constant, and that constant times 1, because t approaches infinity, just means that this expression really is going to be f sub a over k. And see how helpful this expression was? If we had multiplied this whole thing out, it would have been really hard to identify. It would have been much harder to identify that you'd get f sub a over k in the long run, which means that we're going to get a final result that kind of looks something like this. Not really, but we're just going to kind of graph it out. And what we're going to do is kind of graph it like this. And we're going to have, as it approaches infinity, it's going to reach. I know I didn't draw the line. The line should be much closer to this curve, but we're going to reach f sub a over k. I know I didn't make that apparent, but I think you guys can get that point. And that's how you would graph this. And I think that should be it for problem number 2. Now let's move on to problem number 3 once I'm able to erase all of this. Alright, last but not least, we have problem number 3. So, a disk of mass m is equal to 2 kilograms and radius r being 0.1 meters is all supported by a rope of negligible mass. Alright? As shown above, the rope is attached to the ceiling at one end and passes under the disk. The other end of the rope is pulled out upward with a force of F sub a. The rotational inertia of the disk around its center is mr squared all over 2. Calculate the magnitude of the force F sub a needed to hold the disk at rest. Okay, so this first problem isn't so bad. What I drew here is a little diagram, if you would call it a diagram. So you have mg going down, and you have F sub a pulling up. And so basically what I did was I treated it as a particle mass, or a point mass, I guess is what you should say. And because for the force needed to hold the disk at rest, your F net has to be 0. In other words, your F sub a and your mg need to be equal to each other. So let me just write that out. So we have F sub a, and let's see, can I actually get this to work? Come on. Here we go. Okay, and yes, even though it looks like an eraser, it's not an eraser. Alright, so we have F sub a is equal to mr squared over, whoa, wait, what am I doing? No. Sorry, that's a bad Muhammad. Not doing the right thing. Alright, this is actually just equal to mg, right? Yeah, from the free body diagram. Now, all we need to do is plug in our values. So, F sub a, they said was, not F sub a, the m is just 2. Gravity is 9.8. I don't think you should use 10 on the free response, just to be safe. Divide that by 2. And, wow, this actually works pretty nice because 2's cancel out, so you actually do get an answer of 9.8 newtons. And make sure you include units. That's always important. But I think they still accept 10 meters per second squared or 10 newtons for this answer. But just to be safe, you might want to do that. And it's still green, but I really don't care. So what are they asking? At time t equals 0, the force F sub a is increased to 12 newtons. I don't know why I highlighted that, but which causes the disk to accelerate upward. The rope does not slip on the disk as the disk rotates. So now it's asking for the linear acceleration of the disk, which, if I do recall correctly, that requires us to do that long-winded thing Wilkie taught us in class, where you have to put in your Greek to normal lettering, or normal letters. I don't know if lettering is even a word.
Okay, so first I would go about by writing F net equals MA. I guess you can put lowercase m, it doesn't really matter. And so the thing is, at time t equals 0, before anything starts, this force is increased to 12. So let's just put 12 Newton. So it has an initial. So that means the F net is not 0. So that means the disk is moving up. All right. So that means that we're going to have a torque because we have an initial force. And because of that, I guess we can write, let's just write F sub A like that. And so we can write that as 12 newtons, if that even looks like 12 to you. Yeah. I'm going to go with variables on this one because I think that's a lot easier than just plugging in numbers. But anyways, we have our mg here. Now, please, please, please be mindful that your mg is not perpendicular to the circle or object at hand. And because of that, it's not going to be included in torque. So that means we basically now we just have this tension force. I guess you would have this tension force. So you have some sort of tension force kind of just pulling you down. So I'm going to call that TR. And yes, this is going to be R times F, but you really don't include that in the free body diagram. You just include the force. I'm just including it because it's going to help me. Okay, so we know that F net equals MA. Well, what else is F net? Didn't we already solve that earlier? Turns out F net is also equal to FA plus the tension, all right, which is also subtracted from by mg, and I don't know if you can read that, which is all equal to ma. Now, you might be wondering, okay, I get that part where F sub A comes in and mg is being subtracted because we already talked about that up here, but where did you get the tension force? Well, the thing is, once you have an initial value of 12 newtons, the thing is accelerating upward, but that also means there's a tension force that exists here. Initially, we had nothing. We had no acceleration before. I shouldn't say no force from before, but initially, for problem A, for part A, we didn't have any acceleration. So, I mean, there's really no tension there to begin with. But now, because we have it, and I think this is a pretty tricky problem, honestly, but you're going to have to include that tension somehow. All right, that's just going to come with F sub A, and that's going to be pointing upwards. So that's kind of its own quantity, I guess, if you want to call it that. And mg is just pointing downwards at this point. Because you're also, if you really think about it, you're not only are you pulling up with the force, it's kind of hard to explain, but you're also making it spin at the same time. And that tension force kind of goes into play there. Alright, so now we also know that, can I extend this page? Yay. Okay. We also know that, this is kind of important to note, the sum of the torque is equal to rotational times alpha, and from here it's just review. I go into really deep detail about these things, but I shouldn't be. I'm just gonna skip along here. So we know that from our previous free body diagram, the F sub A times R minus TR is equal to, well, we have I, and I is a rotational inertia. Well, lo and behold, that's what we were already given that in the problem, which is pretty nice. All right, yeah, you know what? I guess I can just put a 2 over that. I don't know why I'm doing that. Okay, so now we have this times, and I'm going to save myself a step. This is just A over R multiplied times A over R. And remember, we're trying to solve for acceleration. So, well, I guess we're running into a roadblock here. because, oh, okay, well, first of all, before I even do anything, can we just cancel out the r's? That's just something we've learned, and I think it'd be very nice if we just do that. Okay, r's are all canceled out. That's great. But the thing is, we really have no idea what the tension is. I mean, you can plug it in with the actual values, but I'm just going to use the variables. So we're trying to get rid of the tensions. And so we have one equation here, and we have another right here. Well, I'll use purple for this. So now, so if we're going to solve for tension, tension would be equal to m times a. Well, that'd be plus mg minus f sub a. So when we plug this in, we get f sub a minus t. Well, t is ma minus mg. And yes, these are two of the small m and big M are literally the exact same thing. I'm just being a little lazy here. F sub a. Okay, great. So now we have ma all over 2. Okay, this is becoming a lot simpler. Now these two are going to go away because that'll just lead to 2f sub a minus ma minus mg. Alright, so let's see what we need to do now. Well, we can do is, we can add this ma to the other side, right? Because we're solving for a, let's get all our a's onto one side. So 2fa minus mg is equal to 3ma over 2. Right? That's 1.5, you're adding, yeah. So now we solve for a. Well, I'm just going to plug in the numbers, and so 2 times fa, well, we're given that was 12 minus m. Well, big M, we were told that's 2. Gravity is 9.8. You can use 10, but I'm just going on the safe side. 3 times 12 times your acceleration, which is what you're solving for to begin with. And if you solve all of that, I'm just going to spare ourselves the time. We have 1.47 meters per second squared, and that's what you should get for part B. All right, I think the only issue with this problem is kind of just setting up this formula right here. And, you know, the thing you really should consider, like, I don't know, I guess I'm trying to explain in my own words. So, I guess what would confuse most people is that having the tension added here. But what you have to realize is if you're pulling upwards too, you're also having a tension force right at this point. Right there. That's another point where you're having your tension. So the string also has tension as well. And I mean, you can add that on there. I don't, even intuitively, even if you had no idea if you should add it or subtract it, I mean, you know, you should, mg is really the only thing that's going to be pointing down anyway, so. Okay, so now that's part B. Now we're doing part C. All right. So this one looks a lot simpler. I think we just need to remember some old formulas, I guess. Okay, the angular speed of the disk at t equals 3 seconds. So when they give you time, when you know time and you know your acceleration, and I think by this time you're going to have enough information to answer the question anyways. We know the linear acceleration is 1.47 meters per second squared. And we also know that when we also know that I think, yeah, the angular speed, I think we can assume to be 0, because even though you have a force initially, I mean, it doesn't really matter. I think it's still going to be 0 anyways. So now you have 3 variables, and all you need to do is convert this to angular acceleration. So in order to do that, you literally just divide by the radius. So divide by r. So really, I think the best one would be WF equals W sub 0 plus alpha t. And, you know, the radius there, it's already given you 0.1. So you're going to plug that value into here. Your time is going to go here. 0 is just 0. So now all you would literally do is plug all that in. So WF would be equal to, I think here, I don't think I put this in my calculator yet, but here, let me plug this in. All right, so I think this is going to be 44 radians per second. Yeah, 44 rads per second. Awesome. All right, so that's part C. And then again, you have to... All right, finally to it. The second to last problem. And I'm going to try opening a new file because I know that's not working. Yeah. Okay, all right. So we're at part D. We're almost there, guys. Calculate the increase in total mechanical energy of the disk from t equals 0 to t equals 3. Okay. So when I see an increase in total mechanical energy, or anything with energy for that matter, the first thing I usually do is write the grand equation that we all know and love. So, delta E is equal to, and this is a variation of the KEI plus KE, or PEI equals KEF plus PEF. This is a variation. I'm looking at everything in the system. And I think this was something that was on the free response for gravitation. So we have delta U G plus, well, we have delta K. Those don't look like deltas, they look like mounds, but gumdrops, but okay. So I'm writing U sub G because that's just a variation of PE. You can call it PE. In fact, you can just do PE, delta PE. And K is that's just kinetic energy in total. The thing here, though, and I think this is pretty important to understand, is that we don't have just one form of kinetic energy, all right? We have multiple versions. What do I mean? Well, not only is the sphere moving up, it's also being rotated at the same time. So I think that's just an important fact to consider. So you need to also have KE rotational and KE regular. You're just your average KE. Okay, I've been saying KE a lot. Okay, so let's do this. So we know that, so I'm going to just write a little separate column here. I think this is what the College Board, I think this is what they usually do. They just writing it like this. In fact, you know what? Let's scratch that. I'm going to write it complete, the whole set. So just so that we're clear. Delta PE plus KE rot plus KE trans blah blah blah, you know. Now we have so now we just need to simplify things. So what do I mean? Well, delta E, I'm just going to put an equal sign so we don't say. So we have M G H, and we also have plus 1/2 mv squared, and we're looking at delta V, but note that we're starting from rest. Even though, again, like I said before, even though you have that initial 12 newtons right when it starts, I mean it really is just 0. So we're just having, that's our VF off the bat. So we don't have an initial of some sort. So now we're looking at that plus, oh, that's a weird color. Plus, oh, shoot. Yeah, I kind of switched things, but that's fine. So we have 1/2 I W squared. All right. So now, first problem. I think this is the hardest part of this problem. How do we convert H? We have no idea. How do we even find that? It's kind of the weird thing. Now, this might sound a little weird, but I think we need to use a kinematic here because there literally is no other way to find how this thing is going to change. So what I'm really saying is we know acceleration. Oh, I made a new file, so it doesn't show, but we already know acceleration was 1.47 meters per second squared, I believe. We have the time. And so what really clicks is, wait a minute, if I have all that, and I'm looking at this as a point mass, again, we're not looking at any rotational thing, can't I just write it like this? mg 1/2 at squared. Now let me explain. We get the 1/2 at squared from delta y equals, or delta h, whatever you want to call it. So we have VIT plus 1/2 at squared. Now we're reminded that VI is just 0, so that goes out. So that just substitutes back in. Okay, cool. We just need at this point, t equals 0 has no impact. We just need to find a way to be able to plug in t equals 3 and find our delta E, and then we're good. So 1/2 m. All right. Sounds good so far, but we don't know the velocity. But what we do know, we know the rotational, we know the value for the rotational velocity. Yeah. I don't know. I'm stuttering a lot. W squared plus, okay, so now I'm going to write this down here, but 1/2 I, well, we're given that 1/2 mr squared over 2, or you can have that as the whole thing, it doesn't really even matter. 1/2 mr squared, now W squared, be mindful that we still know W. We don't have to, I don't think we need to convert Greek for this. So I'm just going to kind of separate this. So now I'm going to extend the page. Okay. So I think it's at this point, I mean, you can probably simplify this. You can probably go on and say, you know, I'm going to combine these mr squared. I'm going to do something. These two are the same, by the way. Don't worry. We're going to combine the mr squared, you know, mr squared, W squared. We're going to change it to 1/3 or 3/4. But I'm just going to plug in everything the way it is. And this is going to get a little messy, but here we go. So we have 2 times 9.8 times 0.5 times 9 point, or not 9.8, 1.47. Sorry. 1.47 times t, which is 9, right? That's just 3 squared, plus, well, I'm going to write this underneath 0.5 in all parentheses times 2 times, well, r is just 0.1 times w, or omega. So where do we find this value? Well, if we do recall that we just find the angular speed. They kind of set up the problem for you, really, at t equals 3 seconds. So we calculated that. I think that was, let me check on my calculator. 44, right? So we're at 44. So let me check on my calculator. So let me check my calculator, and I think that was 44 radians per second. Yeah, 44 radians per second. Cool. Now we have yeah. And then we add that to plus 0.5 times, well, that's just 2. This is all including the parentheses, times our 0.1 squared. So really this is just plugging and chugging. I mean, at this point, you should be able to do this. Times, that's not a plus, sorry, 44 squared. Okay, out of that whole mess, you should get, as a final answer, delta E is equal to, come on, be green, green, yes, green, good, green, all right, 159, and it's not green, all right, I don't care. Well, no, can it, yay, okay, I'll write it in green just so that we're cool. This is our final answer. In joules, we have 159 joules. And that should be our answer. Okay. So now we have the question. The disk is replaced by a hoop of the same mass and radius. Okay, so kind of getting memories. See, the best part about this entire free response is that they didn't ask you to derive the rotational inertia. It's drag and deriving rotational inertia. Indicate whether the linear acceleration of the hoop is greater than, less than, or the same as the linear acceleration of the disk. Okay, now here's the thing. We know that a hoop, in terms of placement of mass, is going to be much more varied. It's going to be much more different than this. So in terms of rotational inertia, I mean, this one's going to have a higher rot I, I'm going to call it. And this one has a slower value for the rotational inertia. So, because of that, because we have a higher rotational inertia, since, okay, if we also, okay, here's another thing. If we remember, for the rotational inertia of a hoop, it's just mr squared. This thing is mr squared all over 2. So they have the same mass and everything, but when you really consider it, the linear acceleration of the hoop is actually going to be greater. Pause. Because it has a higher rotational, so because it has a higher rotational inertia, all you're going to need to do, I mean, it's just less than. I don't think we really need to argue about that because it has a higher rotational inertia, it resists angular acceleration more. I mean, that's by definition what rotational inertia is. So mr squared over 2 is less than mr squared. And this is for the sphere. It's the disk, sphere, whatever. Disk, hoop. And you can just talk about the mass. You can talk about the placement of the mass. But if you remembered how you derive both of these, I mean, that should be pretty easy. So because it's smaller, it resists angular acceleration less, which means it's going to spin faster, which means that the linear acceleration is going to be of the hoop will be less than the linear acceleration of the disk. All right. And that's it. I know I spent a long time on this free response. Normally speaking, I mean, again, it's like the video I posted for the multiple choice. I would never go into detail with this on the actual test. I mean, you're given 15 minutes per section. Whoops, I should have never done that. You're given 15 minutes per section, so you really have to keep your time in check. I mean, I think free response, it's just timing. And you don't need to get all of these right. All right? I mean, getting a 5, it's not too hard getting a 5. To get a 5, I mean, if you ace the multiple choice, which is not hard to do, and then for the free response, you get most of them right. And sure, you could probably, like, to be honest, I don't think this part was too bad. But I think the part where you had to add plus t to the FNet formula, the net formula. I think that was pretty difficult. All right, well, thanks for watching. Maybe I'll make another video. Who knows? Thanks.